Hello guys! Today we'll be doing the second De Morgan's Law and introducing index sets and kind of extending De Morgan's Law to index sets as well. But first, let's start with number 2. In my previous video I proved number 1, so we'll be assuming that this is true because it is, and I will not prove it again because I have a whole video dedicated to that. So, if we sub in, using this we can say that, in fact I'll do it again. The complement of, now for A, I'll just let A equal to the complement of A. So the complement of A, union, well I have to sub in the complement of B now, equals, well, if we sub in the complement of A into A, we get the complement of A intersect the complement of B, which equals, well, the complement of A is just A. Okay, we've established this in another video. So this is just A intersect B. Okay. And now, taking the complement on both sides again, leaves us with the complement of A, it's a lot of complements, union the complement of B. How many brackets do I need? 1, 2. 1, 2. Yeah, I think that's enough brackets. Equals. Okay, why not? The complement of A intersect the complement of B. 1 bracket. Which equals the complement of A union B. Well, okay. These two complements will just cancel, and we can just ignore this line of working, it doesn't really matter. Which leaves us with the complement of A union the complement of B equals the complement of, intersect, not union. Intersect. So, yeah. The complement of A intersect B, okay? Which is what we stated there. So, that's both of De Morgan's laws proven. Now, hopefully, I can also give you an intuition about indexing sets within 15 minutes. Right. Let's just tick this off our checklist. Now, what is an indexing set? Well, I'll just give you an example using the union set operator and the intersection set operator. So, let A sub I, not the complex number, just some number, A sub I equal the set of negative I and I. I find drawing this set brackets hard, but okay. So, for example, if we sub in E, this implies that A sub E, as in the number E, equals the set negative E and E. Okay, just as an example. So, let's take the union from I equals 1 to infinity of A sub I, and the intersection from I equals 1 to infinity of A sub I. Now, okay, let's write out some terms. And also this union and this intersection is like the sigma symbol. It just implies that it's the natural numbers from 1 to infinity, not all the real numbers. So, Anyway, A sub 1 is the set of -1 and 1. A sub 2 is the set of -2 and 2. And well, what's the union? It's just all of these sets. If you put them together, what do you get? And well, we get all of the integers except for zero. We get -1, -2, -3. We get 1, 2, 3. But we just don't get 0 because we're starting from 1 to infinity. Okay? And what's the intersection? Well, the intersection is even easier because basically all it is what's in common with these sets? Well, nothing. None of these sets have anything in common. We could keep going down and down. We'd find nothing in common. So it's just phi, an empty set, nothing. We denote this with the Greek letter phi. So that's just a little intuition and a small example. But then you might think, well, isn't the intersection always just going to be nothing? Well, no, I'll give you an example where it's not nothing. So instead of A sub I being the set from -I to I, A sub I can be the closed interval from -I to I, which implies that A sub E, again the number, equals the closed interval from -E to E, which equals the set of x such that -E is less than or equal to x, which is less than or equal to E. Or basically just all of the numbers between -E and E. Natural or integer or non-integer. Okay. So, the union from I equals 1 to infinity, well, A sub 1 equals the closed interval from 1 to the order is important because if it was 1, -1, that would mean it's from 1 to -1. But here it says -I to I, so -1 to 1. A sub 2 is the closed interval from -2 to 2, and so on. So the union from I equals 1 to infinity of A sub I equals, well, here 0 is included, along with all of the natural numbers, all of the real numbers, not natural numbers, all the real numbers, because this includes decimal points, irrational numbers, everything between -1 and 1. And as this goes down to infinity, we're eventually going to hit on all of the real numbers, or the real line. Okay? And this includes every number on the real line. However, the intersection from I equals 1 to infinity of A sub I equals, well, if we look at the terms, now there is something in common, because within this, there is also the closed interval between -1 and 1, somewhere within this interval. So, as we keep going down, this interval here, this closed interval, will always be common in all of the sets. So, this is not equal to nothing. This equals the closed interval from -1 to 1. Okay? So that's just a little intuition. Now, gotta go fast. Okay, I've been informed I've got 5 minutes. So, to prove this, we'll do the first half in blue, the second half in black. So, let X be an element of the complement of the union from alpha, the union over alpha in I of A sub alpha. This is just alpha in some index set I, basically. Which means that X is not an element of the union over alpha, an element of I of A sub alpha, which means that X is not an element of A sub alpha, which means that X is an element, of the complement of A sub alpha, which means, and this is for all alpha in I, so all alpha, all of the sets, all X has this in common, so this implies that X is an element of the intersection, because it's all of the alpha in I, for alpha in I, of the complement of A sub alpha. Because this is basically saying that X is always going to be the complement of A sub alpha. Which means, therefore, that the complement of the union over alpha in I of A sub alpha contains the intersection over alpha in I of the complement of A sub alpha. Now we're going to do the same thing, but in black, so that it's clear that we're doing different thing. Different X is an element of this, the intersection over alpha, an element of I, of the complement of A sub alpha, meaning that X is not an element of A sub alpha, for alpha is always an I, which means that X is not an element of the union over alpha in I of A sub alpha, because X will never be in alpha by definition. Not just the intersection, but the union. It will never be in alpha, meaning, of course, by definition, that X is an element of the complement of the union over A in alpha of A sub alpha. And because of this, we can therefore say, now we'll write it in red again, the complement, the intersection over alpha, an element of I, of the complement of A sub alpha contains the complement of the union over alpha in I of A sub alpha. Okay guys, thank you guys for watching. Hopefully I'll upload tomorrow again. Hopefully you get a good intuition of index sets, and I proved the second one. Let's tick this one off our list. Goodbye, thanks for watching.